Now that we can rank things according to atomic size, we can use that to go ahead and rank atoms by other properties as well. Ionization energy is an important property that has to do with how much energy it takes to rip an electron away from an atom. Here we have a hydrogen atom, and we're taking away its only electron, and we're left with a hydrogen ion. Got to be doing this in the gas phase. This is the kind of thing that happens in that discharge lamp that you saw in the line spectrum lab. This is one of the many processes that are happening inside that lamp. That's ionization. You're turning an atom into an ion. And ionization energy is the amount of energy that that reaction takes. Now, if this is a chemical reaction with moles in it, we can say it's the energy required to remove a mole of electrons. From a mole of gas atoms. There is kind of a mole-based definition for ionization energy. You can do it atom-based too. You can say it's the energy required to rip one electron away from one atom. You're going to get different units that way, though. If you do it this way, usually they put the ionization energy in kilojoules per mole. And if you do it in terms of atoms, it'll probably just be joules. And we happen to know what the ionization energy for hydrogen is. Remember the Rydberg constant. The ionization energy for hydrogen is going to be the energy of the highest possible state, which is 0, minus the energy of the ground state, which is minus 2.18 times 10 to the minus 18. So the ionization energy for hydrogen is going to be just equal to the Rydberg constant. The Rydberg constant in joules is the ionization energy for one atom of hydrogen. Anyway, you can do this for other atoms too. If I look at the first ionization energy for helium gas, I'm going to get a helium positive ion here, plus an electron in the gas phase. Now suppose I compare the numbers for those two things. Let's picture what's going on. With this first reaction, we have a proton in the nucleus, and the electron is out here, and I am yanking that electron off. In the second process, I have a +2 charge on the nucleus, because this has atomic number 2, and I have 2 electrons, and I am yanking one of them off. Which one's going to be easier? Well, I think this one will be a little bit easier in one sense, in that you're only pulling it away from a +1 charge. It's going to be harder to pull an electron away from a +2 charge, right? So I would expect this to have a higher ionization energy than this one over here. You also, though, have this other electron in there, and electrons hate each other, so they are repelling each other. So it's pushing it out. It's pushing it away. The nuclear effect is going to be the stronger of the two. Okay, are you confused? Well, there's an easier way to think about this. Let's think about the sizes of the atoms. Here's our periodic table. And remember, we go bigger going to the left and bigger going down. So overall, bigger is this way. Okay, what's going to be bigger? Here's hydrogen and here's helium. Well, according to my trend here, the helium is going to be the smaller. It's going to be smaller than hydrogen is going to be. So if I compare the sizes, I can pretty much figure out what the ionization energies are, or how to compare them anyway, which one's going to be bigger. So if you get a bigger size going down like that, smaller atom gives you a higher ionization energy. So ionization energy goes the opposite way. It's going to get bigger the closer you get up to that corner there. So let's compare a couple of atoms. Let's suppose I've got, I don't know, let's say barium, sulfur, and oxygen, and bromine. And I want to order these by increasing first ionization energy. The first thing I want to do is figure out the size trend. And how did I do that? Well, I'm going to look at where these things are on the periodic table. Okay, so here's sulfur. Let's sketch a periodic table here. Sulfur's there. And let me see, barium. Barium is down here. And oxygen. Oxygen is up there, above sulfur. And what else do we got? Bromine. Bromine is down here. Alright, so our size trend is going to be bigger getting down the closer you are to that corner. So it's pretty clear that barium is biggest. Barium is the biggest of the three. It's a little bit trickier over here, right? Generally, as you go down the table, things get bigger. But as you go over, they get a little bit smaller. Still, overall, I think bromine is going to be the next biggest because it's farther down the table than these other ones. It has more shells. Then sulfur is going to be the next biggest, and then oxygen is going to be the smallest. So there's my size trend. So now, ionization energy, this is the biggest, and then this is the smallest. Now the smallest one has got the biggest ionization energy. Okay, so that one's going to have the biggest ionization energy. And then it's going to go in the reverse order here. The biggest one will have the smallest ionization energy. So this is in increasing order because you're starting off with the one with the smallest ionization energy. I'm going to say smallest IE for ionization energy, and this one has the biggest IE. So that's different from size. So you figure out the size trend, which you already know how to do from the last video, and then you just turn it around, reverse it. The smallest becomes the biggest, and the biggest becomes the smallest. So now you can rank things according to ionization energy. Now, let me just say something before we leave. I mean, this is not the only thing you want to see with this. What you should notice is that metals have low ionization energy. And that is why they form positive ions. If they have low ionization energy, it's easy to pry their electrons off, their valence electrons off. So they lose electrons easily. Nonmetals have high ionization energy. They gain electrons easily. They don't lose them easily. And we're going to talk about a property called electron affinity that is going to go along with how much energy is released when you gain an electron instead of losing it. But you can use this as a check on your size trend. Your nonmetals ought to be on the bigger ionization energy end, and they are here, right? The nonmetals are on the right-hand side, and the metals should be on the left-hand side of your ionization energy trend. They have the smallest ionization energy.